Ceramic engineering is the science and technology of creating objects from inorganic, non-metallic materials. This is done either by the action of heat, or at lower temperatures using precipitation reactions from high-purity chemical solutions. The term includes the purification of raw materials, the study and production of the chemical compounds concerned, their formation into components and the study of their structure, composition and properties. Ceramic materials may have a crystalline or partly crystalline structure, with long-range order on atomic scale. Glass ceramics may have an amorphous or glassy structure, with limited or short-range atomic order. They are either formed from a molten mass that solidifies on cooling, formed and matured by the action of heat, or chemically synthesized at low temperatures using, for example, hydrothermal or sol-gel synthesis. The special character of ceramic materials gives rise to many applications in materials engineering, electrical engineering, chemical engineering and mechanical engineering. As ceramics are heat-resistant, they can be used for many tasks for which materials like metal and polymers are unsuitable. Ceramic materials are used in a wide range of industries, including mining, aerospace, medicine, refinery, food and chemical industries, packaging science, electronics, industrial and transmission electricity, and guided light-wave transmission. History. The word ceramic is derived from the Greek word kappa epsilon rho alpha mu iota kappa omicron sigma, meaning pottery. It is related to the older Indo-European language root, to burn. Ceramic may be used as a noun in the singular to refer to a ceramic material or the product of ceramic manufacture, or as an adjective. The plural, ceramics, may be used to refer the making of things out of ceramic materials. Ceramic engineering, like many sciences, evolved from a different discipline by today's standards. Materials science engineering is grouped with ceramics engineering to this day. Abraham Darby first used coke in 1709 in Shropshire, England, to improve the yield of a smelting process. Coke is now widely used to produce carbide ceramics. Potter Josiah Wedgwood opened the first modern ceramics factory in Stoke-on-Trent, England, in 1759. Austrian chemist Carl Joseph Bayer, working for the textile industry in Russia, developed a process to separate alumina from bauxite ore in 1888. The Bayer process is still used to purify alumina for the ceramic and aluminium industries. Brothers Pierre and Jacques Curie discovered piezoelectricity in Rochelle salt circa 1880. Piezoelectricity is one of the key properties of electroceramics. E.g., Atchison heated a mixture of coke and clay in 1893, and invented carborundum, or synthetic silicon carbide. Henry Moissan also synthesized sickened tungsten carbide in his electric arc furnace in Paris about the same time as Atchison. Carl Schroeter used liquid phase sintering to bond or cement Moissan's tungsten carbide particles with cobalt in 1923 in Germany. Cemented carbide edges greatly increase the durability of hardened steel cutting tools. W.H. Nernst developed cubic stabilized zirconia in the 1920s in Berlin. This material is used as an oxygen sensor in exhaust systems. The main limitation on the use of ceramics in engineering is brittleness. The military requirements of World War II encouraged developments, which created a need for high-performance materials and helped speed the development of ceramic science and engineering. Throughout the 1960s and 1970s, new types of ceramics were developed in response to advances in atomic energy, electronics, communications, and space travel. The discovery of ceramic superconductors in 1986 has spurred intense research to develop superconducting ceramic parts for electronic devices, electric motors, and transportation equipment. There is an increasing need in the military sector for high-strength, robust materials which have the capability to transmit light around the visible and mid-infrared regions of the spectrum. These materials are needed for applications requiring transparent armor. Transparent armor is a material or system of materials designed to be optically transparent, yet protect from fragmentation or ballistic impacts. The primary requirement for a transparent armor system is to not only defeat the designated threat but also provide a multi-hit capability with minimized distortion of surrounding areas. Transparent armor windows must also be compatible with night vision equipment. New materials that are thinner, lightweight, and offer better ballistic performance are being sought. Such solid-state components have found widespread use for various applications in the electro-optical field, including optical fibers for guided light-wave transmission, optical switches, laser amplifiers and lenses, hosts for solid-state lasers and optical window materials for gas lasers, and infrared heat-seeking devices for missile guidance systems and IR night vision. Modern industry. Now a multi-billion-dollar-a-year industry, ceramic engineering and research has established itself as an important field of science. Applications continue to expand as researchers develop new kinds of ceramics to serve different purposes. Zirconium dioxide ceramics are used in the manufacture of knives. The blade of the ceramic knife will stay sharp for much longer than that of a steel knife, although it is more brittle and can be snapped by dropping it on a hard surface. Ceramics such as alumina, boron carbide and silicon carbide have been used in bulletproof vests to repel small arms rifle fire. Such plates are known commonly as trauma plates. Similar material is used to protect cockpits of some military aircraft because of the low weight of the material. Silicon nitride parts are used in ceramic ball bearings. Their higher hardness means that they are much less susceptible to wear and can offer more than triple lifetimes. They also deform less under load, meaning they have less contact with the bearing retainer walls and can roll faster. In very high-speed applications, heat from friction during rolling can cause problems for metal bearings, problems which are reduced by the use of ceramics. Ceramics are also more chemically resistant and can be used in wet environments where steel bearings would rust. The major drawback to using ceramics is a significantly higher cost. In many cases, their electrically insulating properties may also be valuable in bearings. In the early 1980s, Toyota researched production of an adiabatic ceramic engine which can run at a temperature of over 6,000 degrees Fahrenheit. Ceramic engines do not require a cooling system and hence allow a major weight reduction and therefore greater fuel efficiency. Fuel efficiency of the engine is also higher at high temperature, as shown by Carnot's theorem. In a conventional metallic engine, much of the energy released from the fuel must be dissipated as waste heat in order to prevent a meltdown of the metallic parts. Despite all of these desirable properties, such engines are not in production because the manufacturing of ceramic parts in the requisite precision and durability is difficult. Imperfection in the ceramic leads to cracks, which can lead to potentially dangerous equipment failure. Such engines are possible in laboratory settings, but mass production is not feasible with current technology. Work is being done in developing ceramic parts for gas turbine engines. Turbine engines made with ceramics could operate more efficiently, giving aircraft greater range and payload for a set amount of fuel. Recently, there have been advances in ceramics which include bioceramics, such as dental implants and synthetic bones. Hydroxyapatite, the natural mineral component of bone, has been made synthetically from a number of biological and chemical sources and can be formed into ceramic materials. Orthopedic implants made from these materials bond readily to bone and other tissues in the body without rejection or inflammatory reactions. Because of this, they are of great interest for gene delivery and tissue engineering scaffolds. Most hydroxyapatite ceramics are very porous and lack mechanical strength and are used to coat metal orthopedic devices to aid in forming a bond to bone or as bone fillers. They are also used as fillers for orthopedic plastic screws to aid in reducing the inflammation and increase absorption of these plastic materials. Work is being done to make strong, fully dense nanocrystalline hydroxyapatite ceramic materials for orthopedic weight-bearing devices, replacing foreign metal and plastic orthopedic materials with a synthetic, but naturally occurring, bone mineral. Ultimately, these ceramic materials may be used as bone replacements or with the incorporation of protein collagens, synthetic bones. High-tech ceramic is used in watchmaking for producing watch cases. The material is valued by watchmakers for its lightweight, scratch resistance, durability and smooth touch. IWC is one of the brands that initiated the use of ceramic in watchmaking. The case of the IWC 2007 Top Gun edition of the Pilot's Watch double chronograph is crafted in high-tech black ceramic. Glass ceramics. Glass ceramic materials share many properties with both glasses and ceramics. Glass ceramics have an amorphous phase in one or more crystalline phases and are produced by a so-called controlled crystallization, which is typically avoided in glass manufacturing. Glass ceramics often contain a crystalline phase which constitutes anywhere from 30% meter per meter to 90% meter per meter of its composition by volume, yielding an array of materials with interesting thermomechanical properties. In the processing of glass ceramics, molten glass is cooled down gradually before reheating and annealing. In this heat treatment, the glass partly crystallizes. In many cases, so-called nucleation agents are added in order to regulate and control the crystallization process. Because there is usually no pressing and sintering, glass ceramics do not contain the volume fraction of porosity typically present in sintered ceramics. The term mainly refers to a mix of lithium and alumina silicates which yields an array of materials with interesting thermomechanical properties. The most commercially important of these have the distinction of being impervious to thermal shock. Thus, glass ceramics have become extremely useful for countertop cooking. The negative thermal expansion coefficient of the crystalline ceramic phase can be balanced with the positive tech of the glassy phase. At a certain point, the glass ceramic has a net tech near zero. This type of glass ceramic exhibits excellent mechanical properties and can sustain repeated and quick temperature changes up to 1000 degrees Celsius. Processing steps. The traditional ceramic process generally follows this sequence: milling, batching, mixing, forming, drying, firing, assembly. Milling is the process by which materials are reduced from a large size to a smaller size. Milling may involve breaking up cemented material or pulverization. Milling is generally done by mechanical means, including attrition, compression, and impact. Attrition milling equipment includes the wet scrubber, which has paddles in water creating vortexes in which the material collides and break up. Compression mills include the jaw crusher, roller crusher and cone crusher. Impact mills include the ball mill, which has media that tumble and fracture the material. Shaft impactors cause particle-to-particle attrition and compression. Batching is the process of weighing the oxides according to recipes, and preparing them for mixing and drying. Mixing occurs after batching and is performed with various machines, such as dry mixing, ribbon mixers, Mueller mixers, and pug mills. Wet mixing generally involves the same equipment. Forming is making the mixed material into shapes, ranging from toilet bowls to spark plug insulators. Forming can involve extrusion, such as extruding slugs to make bricks, pressing to make shaped parts, slip casting, as in making toilet bowls, wash basins and ornamentals like ceramic statues. Forming produces a green part, ready for drying. Green parts are soft, pliable, and over time will lose shape. handling the green product will change its shape. For example, a green brick can be squeezed, and after squeezing it will stay that way. Drying is removing the water or binder from the formed material. Spray drying is widely used to prepare powder for pressing operations. Other dryers are tunnel dryers and periodic dryers. Controlled heat is applied in this two-stage process. First, heat removes water. This step needs careful control, as rapid heating causes cracks and surface defects. The dried part is smaller than the green part, and is brittle, necessitating careful handling, since a small impact will cause crumbling and breaking. Sintering is where the dried parts pass through a controlled heating process, and the oxides are chemically changed to cause bonding and densification. The fired part will be smaller than the dried part. Forming methods. Ceramic forming techniques include throwing, slip casting, tape casting, freeze casting, injection molding, dry pressing, isostatic pressing, hot isostatic pressing, and others. Methods for forming ceramic powders into complex shapes are desirable in many areas of technology. Such methods are required for producing advanced, high-temperature structural parts such as heat engine components and turbines. Materials other than ceramics which are used in these processes may include wood, metal, water, plaster and epoxy, most of which will be eliminated upon firing. These forming techniques are well known for providing tools and other components with dimensional stability, disambiguation needed, surface quality, high density and microstructural uniformity. The increasing use and diversity of specialty forms of ceramics adds to the diversity of process technologies to be used. Thus, reinforcing fibers and filaments are mainly made by polymer, sol-gel, or CVD processes, but melt processing also has applicability. The most widely used specialty form is layered structures, with tape casting for electronic substrates and packages being preeminent. Photolithography is of increasing interest for precise patterning of conductors and other components for such packaging. Tape casting or forming processes are also of increasing interest for other applications, ranging from open structures such as fuel cells to ceramic composites. The other major layer structure is coating, where melt spraying is very important. But chemical and physical vapor deposition and chemical methods are all seeing increased use. Besides open structures from formed tape, extruded structures, such as honeycomb catalyst supports, and highly porous structures, including various foams, for example, reticulated foam, are of increasing use. Densification of consolidated powder bodies continues to be achieved predominantly by sintering. However, the use of pressure sintering by hot pressing is increasing, especially for non-oxides and parts of simple shapes where higher quality is needed, and larger size or multiple parts per pressing can be an advantage. The sintering process. The principles of sintering-based methods are simple. The firing is done at a temperature below the melting point of the ceramic. Once a roughly held together object called a green body is made, it is baked in a kiln, where atomic and molecular diffusion processes give rise to significant changes in the primary microstructural features. This includes the gradual elimination of porosity, which is typically accompanied by a net shrinkage and overall densification of the component. Thus, the pores in the object may close up, resulting in a denser product of significantly greater strength and fracture toughness. Another major change in the body during the firing or sintering process will be the establishment of the polycrystalline nature of the solid. This change will introduce some form of grain size distribution, which will have a significant impact on the ultimate physical properties of the material. The grain sizes will either be associated with the initial particle size, or possibly the sizes of aggregates or particle clusters which arise during the initial stages of processing. The ultimate microstructure of the final product will be limited by and subject to the form of the structural template or precursor which is created in the initial stages of chemical synthesis and physical forming. Hence the importance of chemical powder and polymer processing as it pertains to the synthesis of industrial ceramics, glasses and glass ceramics. There are numerous possible refinements of the sintering process. Some of the most common involve pressing the green body to give the densification a head start and reduce the sintering time needed. Sometimes organic binders such as polyvinyl alcohol are added to hold the green body together. These burn out during the firing. Sometimes organic lubricants are added during pressing to increase densification. It is common to combine these, and add binders and lubricants to a powder, then press. A slurry can be used in place of a powder, and then cast into a desired shape, dried and then sintered. Indeed, traditional pottery is done with this type of method, using a plastic mixture worked with the hands. If a mixture of different materials is used together in a ceramic, the sintering temperature is sometimes above the melting point of one minor component, a liquid phase sintering. This results in shorter sintering times compared to solid-state sintering.